Okay, so as I had already explained, ImageJ is an open source toolbox, and we'll be using that for processing our experimental image data. So this toolbox was originally developed for medical image processing by the National Institute of Health, and it is currently used very widely in the scientific community for simple image processing tasks. So the software can be directly downloaded from the internet, and once we load the software, this is the window that pops up. So here we can see that there are multiple options available, and the file panel here, it basically helps in opening up the image sequence to import the image sequence into the toolbox. So when we store the image sequence from a high-speed camera, say we are performing the recording at say 1000 fps, and we record the video for 1 second. Basically, we have 1000 images saved in a folder from the high-speed camera. So this entire image folder can be loaded into ImageJ. And once we have loaded the image, we can perform multiple operations on it. We can duplicate the imported image stack. We can perform an image inversion. So this is a very interesting operation. So usually in a grayscale image, the highest intensity level 255 is assigned a color of white, and the lowest intensity level 0 is assigned a color of black. During this image inversion, that is reversed. So basically the highest intensity level 255 is assigned a color of black, and the lowest intensity level is assigned a color of white, and proportionally the gray values also change. So this can become helpful under certain conditions, but we won't be exploring this in the current lecture though. And then there are operations that we can perform over the entire stack of images, entire sequence of images that we have imported. So this becomes important, and we will be exploring one of the stack operations. Say we might be interested in getting an average of a sequence of images, or we might be interested in getting a standard deviation of a sequence of images. So there we use these stack operations. And of course we can scale the image that we have loaded, we can crop, we can zoom into a specific zone, we can rename the stack. All these operations can be performed. And then there are operations like filtering, which is very essential, and we'll also be exploring a few filtering techniques. So these are essentially noise reduction techniques. So our experimental data is usually very noisy, and we need to filter out unwanted noise from that for getting useful data. So we'll be exploring a few filtering methods here. And once we have filtered the image, we need to binarize it. So the point of binarizing it is to identify the boundary, is to identify the object of our interest. So here in our case, we are interested in identifying the flame that is actually moving. So basically we need to identify the boundary that contains the flame. So during that process, we will be binarizing the image. And then there are options to add and subtract images. So this is a very important tool, and we'll be using this. And this is again very important because our data is noisy in nature, so there are background noises, so we need to remove that. So the technique that is usually used is to take our image and to subtract it out, subtract out the background image from that. We'll be performing that in the further slides. And then there is a panel to analyze the image data. So this comes after we have identified the object of our interest. So once we have isolated the boundary that contains our object of interest, we can use this panel to measure the dimensions of our region of interest, to measure the intensity profile, and functions like that. We'll be looking into a few of these. Additionally, there are plugins that can be downloaded, and plugins and macros that can be downloaded, and they appear in this panel. We won't be using any of these in the current lecture. So in the bottom panel, we will get an information regarding the pixel, the coordinates of the pixel at which our cursor is present, and also it shows the total number of pixels in the horizontal and the vertical direction. Along with that, there is a toolbox. So this toolbox has options to draw a line, to draw a rectangle, to draw ellipse, polygons. So the idea behind this is to draw a region of interest across which we are going to perform further post-processing operations. Again, we'll be using one of these, and we'll demonstrate this in the further slides. And again, there are options to zoom in, to pan the image, and we'll look into a few of these in the further slides. Okay, so as I had already mentioned, we can load a stack of images or a sequence of images from a folder directly into ImageJ. So we can use the file panel, and from import we can select image sequence. And once we have loaded the image sequence, we can play the image sequence at a specific playback rate using the play button here. We can even change the rate at which we play this animation video. So for that, we can go to the image panel under stacks. So there is animation, and then there is animation options where we can change the playback rate. So this helps us to just view the image sequence in the form of a video, in the form of an animation basically. And once we have loaded the image sequence in a panel, we can see that this is the information regarding the image sequence that has been loaded. So here it shows that this stack essentially has 325 images, and the image that is currently being displayed is a 50-second image. This is the name of the image stack that has been loaded. Basically, this was the name of the folder from which this image stack was imported. And here this shows the scale in metric unit, and this shows the scale in pixel unit. So basically what this means is that 1.01 inches is basically equal to 1080 pixels in the current case. So this is a scale which can actually be changed, and I'll show in the further slides as to how to change the scale. Also, we can see that the loaded image set is 16-bit. It is 16-bit and it is grayscale in nature. Again, like this image type can also be changed. We can change the image type to say 8-bit as well. But there is an option for that. Under the image panel, we can select type and then we can change the image type. Okay, so now to proceed with further processing of our image data. If we look into the animation of our the loaded image sequence, we will see that the flame is actually confined to a very small region in our image. So processing the entire image is of no use. So what we do is we use from the toolbox, we draw a rectangular area of interest in our image where actually the flame is present. Once we have this rectangular box loaded, we can then duplicate this stack using this rectangle as the boundaries. And once we do that, we basically create a new stack that is confined within that rectangular box. The idea behind this is that we'll only be performing the further post-processing operations on this smaller region. Because performing them on a larger region takes up more computational time. So we can see that the cropped image sequence, whatever we have here, it is highly noisy in nature. For example, there are pixels here which are always at high intensity whether the flame is present or not. So these are essentially the background noise, and this needs to be eliminated from our data so that we can process it. So the most common technique that is used for background subtraction is to select a background image and then subtract out the background intensity from the noisy signal. So to do that, we first need to make a background image. Usually in experiments, a background image is taken so that post-processing can be done. But in our case, we don't need to take a background image, and the background image is already present in this stack of images. we can see that here that the flame is present only for a very short sequence of time. For majority of the time the flame is not present, and when the flame is not present it is basically just the background. So from this sequence of images whatever I have loaded, I can basically select a subset where the flame is not present, and that is essentially my background. And once we have that background, say basically we have selected the sequence of images where the flame is not present, and since this is basically a background noise, we need to there are variations between the images within the subset itself. That is because noise is essentially random in nature. So to get an average profile of the background noise, what we need to do is that we need to take the average of all this small subset that we have taken. So here the small subset starts from 1 to 16. So from the image sequence from 1 to 16, basically the flame was not present. So that basically means that that is essentially the background, and we are going to average out the intensity, average out the intensity across each pixel over this entire stack of images. So that is what this operation does. So we go into image panel, into stacks, and then Z project, and in Z project we select the option of average intensity. So this basically gives us an average image of all those 16 images. Basically it gives the average of those 16 images where the flame is not present, basically the average of the average of all the background images. So once we have generated this average background image, what we can now do is we can use that average background image to subtract out the noise data from the image data, from the original image data. So again for that we can perform this subtraction operation. So we can go to process, and then in process we can go to image calculator, and in the image calculator we can select the operation of subtract. And now we can perform the subtraction operation of the noise from the original data, and whatever is the resulting image sequence that we have, that is shown here. So we can clearly see that the image quality has significantly improved. The region where there was high intensity pixels, whether the flame was present or not in the cropped image, is currently not there, and that is because the background noise has been removed. So this is basically an image where we have subtracted out the background. So we can see that even after subtracting out the background, there are regions where the pixel intensity randomly shoots up. So these are isolated regions. They are regions which are away from our main flame boundary, but their pixel intensities randomly shoot up. And these are again a kind of noise, and they need to be removed. And it is very essential to remove this noise. That is because in the further steps we'll see that we are going to isolate the flame boundary based on an intensity threshold. And if there are pixels where the intensity is very high, pixels which are disconnected from the flame boundary where the intensity is very high, the algorithm will map that point also as a part of the flame boundary when it is ideally disconnected. So it is very important to remove these pixels that randomly shoot up, where the pixel intensity is randomly shoot up. So here we are going to use filtering techniques for that, and here we'll use two filtering techniques. One is the averaging filter and the other is a median filter. So in the averaging filter, basically the function creates a bounding box and then changes the pixel intensity values at all pixels in an image. So here I have basically shown a schematic of a 3x3 averaging filter. So basically what this does is that it basically creates a bounding box with 3 pixels along the horizontal direction and 3 pixels around the vertical direction. And then it centers this bounding box around the pixel where the intensity value needs to be changed. and then it estimates the average intensity of all the pixels in that bounding box and then assigns that particular average value as the new intensity at this location. And then next, the sliding window moves to the next location and basically traverses all the pixels in that image, essentially changing the pixel intensity for all the pixels in that image, and it generates a new image. So that is what happened here. So basically this was the original image with the background being subtracted, of course. And after we do a 2x2 pixel averaging, this is the flame image that we end up with. And after we do a 4x4 pixel averaging, this is the flame boundary that we end up with. So we can see that whatever were the random pixels where the intensity was shooting up before filtering, the intensity levels have actually reduced after this averaging filter. Now we'll explore another filter which is called as a median filter. Averaging filter is very similar to the median filter, except that instead of taking the average of all the pixel intensities in that bounding box, it takes the median of the pixel intensities in that bounding box. So again, here I have shown a 3x3 median filtering. So again, the bounding box has 3 pixels along the horizontal direction and 3 pixels along the vertical direction. And the bounding box is centered around the pixel where we are changing the intensity currently. And it sorts basically all the pixel intensity values and then identifies the median value and then assigns that obtained median value as the new filtered value of the intensity at that pixel. And again, this bounding box traverses across the entire image, changing the pixel intensities at all pixels, and it generates a new image altogether. Again, we can see here that this was the original image before filtering, and this is the image that we obtain after 2x2 median filtering, 2x2 pixel median filtering, and this is the image that we obtain after 4x4 pixel median filtering. Again, we can see that the points where the intensities were randomly shooting up, they have been removed to a great extent. But a very important problem has also been introduced because of this filtering, and that is that the boundary of the flame has been blurred. Initially, the flame's interface was a little bit more sharp, but after this filtering using the median filtering or the mean averaging filter, what we have essentially done is that we have blurred out the boundary of the flame. However, we'll tackle this problem next when we identify the flame boundary using the thresholding technique. So once we have filtered the image, we now need to identify the boundary of the flame. We already saw that when we use this filtering technique such as average filtering or median filtering, we essentially blur the boundary of the flame. Now to capture the boundary back, to get the effective boundary of the flame, we are going to use this thresholding technique. So thresholding is essentially, it basically converts our grayscale images now into a binarized image. So the technique of creating this is quite simple. So basically I decide a cutoff value, say here the cutoff value is 124. So that means that all the pixels with intensity value greater than this 124 will be assigned a binary value of 1, and all the pixels with intensity less than this value of 124 will be assigned a binary value of 0. And all these pixels which are identified by the binary value of 1, they'll be called as foreground. The class will be called as foreground. And the class of pixels which are identified by the binary value of 0, they are called as background. So this is the essential idea behind this thresholding, basically to convert a grayscale image into a binary image. So this can be done in multiple ways. So here actually I have shown a histogram of an image. So we can see that say from 0 to 255 intensity levels, what are the number of pixels that is associated with each level. For example, at an intensity level of 124, we have approximately 500 pixels. So this is basically the distribution of pixels across different intensity levels. And once we choose a threshold value, everything on to the right side of this threshold will be assigned a binary value of 1, which basically becomes the foreground, and everything on to the left hand side will be assigned a binary value of 0, which is basically the background. Now this cutoff or this threshold value can be chosen in multiple ways. So we'll explore three techniques here. So one is a mean thresholding. So in mean thresholding, what we do is that we take the average of all the pixel intensities in an image, and then we use that mean to separate out the foreground and the background. So if the mean value is say say ik, so we say that all the intensities which are greater than ik will be class 1, which is basically foreground, and all the intensities which are lower than that mean value, which is again ik, so that will be basically the background. And there is another thresholding technique that we can use, which is basically the percentile thresholding. Say here again, I'll explain this with an example. So if I say that I'm going to do a 2% percentile thresholding, what that means is that the two brightest 2% of the pixels which have the brightest intensity will be assigned into the foreground category, and the rest 98% of the pixels will be assigned to the background category. So only the brightest, the top two brightest pixels will be categorized into the foreground and will be assigned the binary value of 1. We'll see what is the effect of using different thresholding techniques. Before that, we'll go into another thresholding technique, which is called as the Otsu thresholding. So this is a very commonly used technique in image processing. So here what we have is that, so here it iteratively estimates this threshold value. So the idea behind this is we start off with an initial guess threshold value, and then we categorize the image into foreground and background. And once we have categorized that, we can calculate the class statistics for each of the foreground and background classes. So we can estimate what is the probability of occurrence for each class. We can estimate what is the mean associated with each class. We can even estimate the standard deviation and the variance within each class. After that, we define a parameter which is known as the weighted intra-class variance. The threshold is iteratively chosen such that this value, which is basically the intra-class variance, is minimized. And mathematically, it is possible to show that minimizing this value of intra-class variance, it basically maximizes the variance between the two classes, which is background and the foreground. So basically, in an iterative manner, the Otsu thresholding algorithm, it chooses an optimum value of threshold where the variance between the background and the foreground is maximized, and the variance within each category, within the background and the foreground category, is minimized. So this is basically the sequence, the images that we get after thresholding. So this is basically the image before thresholding, and this is after mean thresholding. We see that mean thresholding does not do a good work, and then we can do so here I have shown percentile thresholding with 2%. Basically the 2% brightest pixels are assigned value of 1, and this is for the Otsu thresholding. So we see that the Otsu thresholding technique does a pretty good job at capturing the flame boundary. Now that we have actually estimated the boundary of the flame, we have identified our object of interest. Now we can use analyze toolbox to actually capture the parameters such as the flame dimensions and other associated things. So once we have the binarized image, so this is the image sequence that we end up with. So to sum up everything, we started off with a noisy image, then we did background subtraction, and then we did noise filtering, and then finally we did binarization, and this is the image sequence that we finally end up with. So here the pixels only have two values. They can either there can either be of intensity 0 or they can be of intensity 1. They are binarized images. Okay, and now we can use this binarized images to basically isolate the boundary of the flame. Before going into this, I'll show you how to set the scale in the problem. So here basically setting the scale basically means how to change the spatial resolution, or how to change the metric that is represented by a pixel dimension. So here if we go to analyze and set scale, we can change what each pixel is representing. So basically here I'm telling that 12.5 pixels are representative of 1 mm here in my problem. So this is actually constrained by the high speed camera that is actually used to capture the imaging system that is basically used to capture this phenomena. And a calibration is usually taken during the experiments to actually estimate like what is the pixels per mm, and these values are directly imported into this when we set the scale. So once we have actually set the scale, the point of this is that we can now get all the parameters of our interest, for example the dimensions of the flame and all the associated parameters in metric units like mm units or meter units, whichever in which we are interested in. Now we can use the analyze toolbox to actually capture the boundary of the flame, to find out how, and to draw the bounding box around the flame, to estimate how the flame is moving in the sequence of images, and all these operations can be performed. So for that, in the analyze toolbox there is an option for analyze particles, and we can set the thresholds, the lower and upper limits for this. And once we have set that, basically it tracks regions which have intensity, which have area between this lower and upper limits. So here it's set in 0.25 to infinity, and so anything below 0.25 mm square is discarded, and anything which is above that, greater than 0.25 to infinity, is tracked down. And since here we only have one continuous region of pixels which is identified as foreground, it is only going to track the flame boundary. And we can even during this analysis process we can even set like what are the parameters that we are interested in tracking. We might be interested in tracking the area of the flame boundary, we might be interested in the center of mass or the centroid, or we might be interested in the dimensions or the bounding box that encloses this flame boundary. So all these parameters can be tracked across the sequence of images to get a temporal variation of these parameters. Quantities like integrated density do not seem to make any sense in a binarized image. However, I'll show how this can be used to make sense, for example, to get the chemiluminescence data in the further slides. So once we are done with this, we can run this analyze particle for the entire sequence of images, and we can load all the boundary data, the boundary of the flame images that are identified from the binary images into this ROI manager. So this ROI manager contains the information across the entire image sequence, showing where the flame boundary is. Now the very important thing to do here is that once this flame boundary is identified, we need to go back to the original image where binarization has not been performed yet. Because when binarization is performed, all the intensity, all the values within the flame boundary were automatically mapped to a value of 1. So estimating the intensity of the flame based on the binarized image would not make any sense. Whereas if we estimate the intensity of the flame in an original image where binarization has not been done, there would be a gradual variation in the intensity across the flame along the spatial direction. So there integrating the intensity of the pixels across the entire flame boundary would be a representative of parameters such as chemiluminescence, and that is what we are interested in. So that is what we are going to do next. So once we have estimated the boundaries of the flame and captured these boundaries in the ROI manager, we go back to the original image which has not been binarized yet, and we are going to reperform this entire measurement whatever we did on this image sequence which has not been binarized yet. So now once we do that operation, we basically in the results tab we end up with a sequence of results across the image sequence. So each row basically represents results corresponding to a specific image sequence, and it has been performed over all the 325 images that were present in the stacks that were actually loaded up. So once we have this data, we can directly export them into Excel format or CSV format. And once we have that, we can plot them. So here I'll show a plot of how the chemiluminescence, again the chemiluminescence was estimated based on the integrated density. Since we are performing this operation again on images which are not binarized and on the 8-bit images or 16-bit images, integrating all the pixel intensities inside the flame boundary is a representative of the total heat release rate or the chemiluminescence intensity of the flame. So this is how the chemiluminescence intensity profile looks like here. And here I've basically plotted how the centroid of the flame moves following ignition to extension. So we can see that as the flame ignites at a specific location, the chemiluminescence intensity rises, it reaches a peak and then gradually starts decaying down. And during this entire process, the flame upon ignition, it starts to move upstream along the positive x-axis. It then propagates and then at a particular point it extinguishes. So here what we have done is that from the image we have been able to quantitatively track the variation, the temporal variation of a few parameters. So there are many other parameters that can actually be plotted. We can estimate based on this data, we can estimate how the flame shape is varying during this entire propagation phase. And many other parameters can be plotted to get their temporal variations. And all this can be used to make sense out of the data, sense out of the physical phenomena that is actually happening. What we finally see here is that from all the images we are going to extract time series data again, and this is very similar to the data that we get from a pressure sensor or any sensing based devices as well. So in the next portion of this lecture we'll be looking into how to make sense out of these time series data, how to represent them in different coordinate systems so that the analysis becomes easier. So that is what we'll be looking into next.